NENOMATICA, where mathematics meets YouTube excellence. Welcome to this math tutorial on factoring quadratic trinomials using the sum and product method. In this video, we'll learn a systematic approach to factoring expressions of the form x squared plus bx plus c by finding numbers whose sum and product match specific values. The key to the sum and product method is to recognize that when we expand a factored form of x plus q, we get x squared plus p plus q, x plus p times q. This means that p plus q represents the coefficient of x, and p times q represents the constant term. When factoring, we need to find values of p and q where their sum equals the coefficient of x, and their product equals the constant term. Here's the step-by-step process we'll follow. First, identify the coefficient of x and the constant term in the quadratic expression. Second, find two numbers whose sum equals the coefficient of x, and whose product equals the constant term. Finally, use these numbers to write the factored form. Let's apply this method to 3 specific examples. Let's start with our first example. We need to factor x squared plus 2x minus 8. In this expression, the coefficient of x is 2 and the constant term is negative 8. Now, we need to find two numbers whose sum is 2 and whose product is negative 8. Let's list the factors of negative 8, 1 and negative 8, as well as negative 1 and 8, 2 and negative 4, as well as negative 2 and 4. Let's check which pair has a sum of 2. 1 plus negative 8 equals negative 7. That's not right. Negative 1 plus 8 equals 7. That's not right either. 2 plus negative 4 equals negative 2. That doesn't work. Negative 2 plus 4 equals 2. This pair works. Their sum is 2, and their product is negative 8. So, the factored form is x plus 4, x2, or equivalently x2, x plus 4. Let's move on to our second example. We need to factor x squared minus 7x plus 12. In this expression, the coefficient of x is negative 7, and the constant term is 12. We need to find two numbers whose sum is negative 7, and whose product is 12. Let's list the factors of 12. 1 and 12, 2 and 6, 3 and 4. Since we need a negative sum, both factors must be negative. Let's check. Negative 1 plus negative 12 equals negative 13. That's not right. Negative 2 plus negative 6 equals negative 8. That's not right either. Negative 3 plus negative 4 equals negative 7. This pair works. Their sum is negative 7, and their product is 12. So, the factored form is x3, x4. For our final example, let's factor x squared plus 2 square root of 2 times x plus 2. Here, the coefficient of x is 2 square root of 2, and the constant term is 2. Now, we need two numbers whose sum is 2 square root of 2, and whose product is 2. Let's think about this carefully. We know that square root of 2 times square root of 2 equals 2, and square root of 2 plus square root of 2 equals 2 times square root of 2. So the two numbers we're looking for are square root of 2 and square root of 2. Their sum is 2 square root of 2, and their product is 2. Therefore, the factored form is x plus square root of 2 times x plus square root of 2, which can be written as x plus square root of 2 squared. Now, let's summarize the sum and product method with a clear algorithm you can follow for any quadratic trinomial. For a quadratic expression in the form x squared plus bx plus c, first, find all factor pairs of c. Second, check which pair sums to be. Third, if p and q are the numbers you found, then the factored form is x plus p times x plus q. Remember, if the constant term c is negative, the factors will have different signs. And if the coefficient of x is negative, at least one of the factors will be negative. Let's visualize how this method works. We can think of the factoring process as finding the dimensions of a rectangle. If the area of the rectangle is the constant term c, and the sum of two sides is the coefficient b, then those sides represent the factors we're looking for. For example, with x squared plus 5x plus 6, we need factors of 6 that sum to 5. The factors of 6 are 1 and 6 and 2 and 3. 1 plus 6 equals 7, which isn't 5. 2 plus 3 equals 5, which is what we want. So, the factors are 2 and 3, and the factored form is x plus 2, x plus 3. Now, let's check your understanding with a quick practice problem. Try factoring x squared plus x minus 12. Take a moment to work through this on your own. For this problem, The coefficient of x is 1, and the constant term is negative 12. We need two numbers whose sum is 1, and whose product is negative 12. The factors of negative 12 include 1 and negative 12, negative 1, and 12, 2 and negative 6, negative 2 and 6, 3, and negative 4, negative 3 and 4. Checking each pair. 1 plus negative 12 equals negative 11. That's not 1. Negative 1 plus 12 equals 11. That's not 1 either. 2 plus negative 6 equals negative 4. Not 1. Negative 2 plus 6 equals 4. Not 1. 3 plus negative 4 equals negative 1. Not 1. Negative 3 plus 4 equals 1. That's it. So, the factored form is x3, x plus 4. Let's summarize what we've learned about the sum and product method for factoring quadratic trinomials. We've seen how to factor expressions of the form x squared plus bx plus c by finding two numbers p and q whose sum is b and whose product is c. We successfully factored three examples: x squared plus 2x minus 8, which equals x plus 4 times x minus 2. X squared minus 7x plus 12, which equals x minus 3 times x minus 4. And x squared plus 2 square root of 2 times x plus 2, which equals x plus square root of 2 squared. Some important tips to remember. If the constant term is positive and the coefficient of x is positive, both factors will be positive. If the constant term is positive and the coefficient of x is negative, both factors will be negative. If the constant term is negative, the factors will have opposite signs. We have the expression 9x squared minus 9xy minus 10y squared. The first step is to recognize patterns in the expression. We can rewrite 9x squared as 3x all squared. This helps us see the quadratic structure more clearly. Next, we need to find two numbers that multiply to give negative 10y squared and add up to negative 3y times 3x, which is negative 9xy. The numbers are negative 5y and 2y. Now we can factor this expression. We get the product of 3x minus 5y and 3x plus 2y. Let's move on to our second example. For our second example, we have the expression 25x squared minus 5x minus 42. Similar to our first example, we start by rewriting 25x squared as 5x all squared. Now, we need to find two numbers that multiply to give negative 42 and add up to negative 1. The numbers are negative 7 and positive 6. Now, we can factor this expression. We get the product of 5x minus 7 and 5x plus 6. Let's move on to our third and final example. For our third example, we have a more complex expression. The quantity x minus 2y, all squared, minus the quantity x minus 2y, minus 20. In this case, we can use a substitution to simplify our work. Let's set u equal to x minus 2y. Then our expression becomes u squared minus u minus 20. Similar to our previous examples, we need to find two numbers that multiply to give negative 20 and add up to negative 1. The numbers are negative 5 and positive 4. Now, we can factor this expression. We get the product of quantity x minus 2, y minus 5, and quantity x minus 2, y plus 4. We can simplify this further to get the quantity x minus 2, y minus 5, times the quantity x minus 2, y plus 4, which can be written as the quantity x minus 2, y minus 5, times the quantity x minus 2, y plus 4. Let's summarize what we've learned about factoring polynomials. First, identify any common factors and factor them out. Second, for quadratic expressions, look for patterns that can be rewritten in a more recognizable form. Third, use the method of splitting the middle term to find the right factorization. And finally, for more complex expressions, consider using substitution to simplify the problem. Practice these techniques with different examples to become more comfortable with factoring polynomials. We have x squared minus 19x plus 48. First, we'll identify the coefficient of x squared, which is 1. This means we can rewrite the expression as the quantity x squared plus the quantity negative 19x plus 48. Now, we need to find two numbers that multiply to give 48 and add up to negative 19. Let's think about this. The factors of 48 include 1 and 48, 2 and 24, 3 and 16, 4 and 12, 6 and 8. Since we need a sum of negative 19, both factors must be negative. The factors negative 16 and negative 3 multiply to give 48 and add up to negative 19. So we can rewrite our expression as x squared plus negative 16 minus 3 times x plus negative 16 times negative 3. This simplifies to x squared plus negative 16 x minus 3x plus 48. Now we can factor this as x minus 16 times x minus 3. Let's move on to our second example. We have 100x squared plus 40x minus 21. First, we identify the coefficient of x squared, which is 100. We can rewrite the expression as the quantity 10x squared plus the quantity 4 times 10x minus 21. Now, we need to find two numbers that multiply to give negative 21 and add up to 4. The factors of negative 21 are 1 and negative 21, negative 1 and 21, 3 and negative 7, negative 3 and 7. Since we need a sum of 4, we need one positive and one negative factor. The factors 7 and negative 3 multiply to give negative 21 and add up to 4. So we can rewrite our expression as 10x squared plus 7 minus 3 times 10x plus 7 times negative 3. This simplifies to 10x squared plus 7 times 10x minus 3 times 10x minus 21. Now we can factor this as 10x plus 7 times 10x minus 3. Let's move on to our final example. We have x to the fourth minus 17x squared plus 16. This is a special case where we have a quadratic in terms of x squared. We can rewrite this as the quantity x squared to the power of 2 plus the quantity negative 17 times x squared plus 16. Now, we need to find two numbers that multiply to give 16 and add up to negative 17. The factors of 16 include 1 and 16, 2 and 8, 4 and 4. Since we need a sum of negative 17, both factors must be negative. The factors negative 16 and negative 1 multiply to give 16 and add up to negative 17. So we can rewrite our expression as x squared to the power of 2 plus negative 16 minus 1 times x squared plus negative 16 times negative 1. This simplifies to x to the fourth minus 16 x squared minus x squared plus 16. Now we can factor this as x squared minus 16 times x squared minus 1. We can factor further. X squared minus 16 can be written as x minus 4 times x plus 4. And x squared minus 1 can be written as x minus 1 times x plus 1. So our final factored form is the product of x minus 4, x plus 4, x minus 1, and x plus 1. Let's summarize what we've learned about factoring quadratic expressions. First, we identify the coefficient of the squared term and rewrite the expression in standard form. Then, we use the sum and product method to find factors that work together. We'll begin with the polynomial 16x to the fourth minus 52x squared plus 36. Our goal is to express this polynomial as a product of its factors. In our first step, we'll notice that this is a quadratic in x squared. That means we can substitute u equals x squared, which transforms our expression. We get 4u squared plus negative 13 times 4u plus 36. This helps us see the polynomial as a quadratic expression in terms of x squared. For our second step, let's expand the right side to verify. We have 4x squared squared, which is 16x to the fourth. Then we have negative 13 times 4x squared, which is negative 52x squared. And finally, we have 36. So we've rewritten our original expression in a way that allows us to factor it as a quadratic. In our third step, we'll apply the quadratic formula to factor this expression. Remember, we're treating this as a quadratic in terms of 4x squared. We'll split the middle term, negative 13 times 4x squared, into two parts that add up to negative 52x squared, but whose product equals the product of the first and last terms. In step 4, we'll verify our middle term split. The sum of negative 9 and negative 4 is negative 13, and negative 9 times negative 4 equals 36. This will help us factor using the grouping method. In step 5, we factor the expression using grouping. We get 4x squared minus 9 times 4x squared minus 4 equals 0. In step 6, we can simplify further. For the first factor, 4x squared minus 9 can be factored as 2x minus 3 times 2x plus 3, which is a difference of squares. For the second factor, 4x squared minus 4 equals 4 times x squared minus 1, which equals 4 times x minus 1 times x plus 1. Now, let's move on to our second example. For our second example, we'll factor the polynomial x to the sixth minus 7x cubed minus 8. For step 1, we notice that this is a quadratic in x cubed. We can set u equal to x cubed, which gives us u squared plus negative 7u minus 8. For step 2, we'll factor this quadratic. We need to find two numbers that multiply to give negative 8 and add to give negative 7. In step 3, we verify our choice of factors. Negative 8 plus 1 equals negative 7, and negative 8 times 1 equals negative 8. So our factors are x cubed minus 8 and x cubed plus 1. And so our final factorization for the second example is x cubed minus 8 times x cubed plus 1. Let's summarize what we've learned about factoring higher degree polynomials. First, look for patterns that convert the expression into a quadratic. For example, if you have terms with x to the fourth and x squared, it might be a quadratic in x squared. Second, if it's a quadratic in some expression u, rewrite it in the form u squared plus bu plus c. Third, factor the quadratic using standard methods like splitting the middle term or using the quadratic formula. Fourth, substitute back your original variable and continue factoring as needed. These techniques allow us to factor complex polynomials by breaking them down into simpler forms that we already know how to handle. We want to factor the expression a to the fourth plus a cubed plus a squared minus 2a minus 3. Our first step is to group the terms strategically. We'll group the first two terms, a to the fourth plus a cubed, and the remaining terms, a squared minus 2a minus 3. For the first group, a to the fourth plus a cubed, we can factor out a cubed, giving us a cube times open parenthesis, a plus 1 close parenthesis. For the second group, we recognize the pattern a squared minus 2a minus 3, which can be rewritten as open parenthesis, a plus 1 close parenthesis times open parenthesis, a minus 3 close parenthesis. Looking at our expression, we notice that open parenthesis, a plus 1 close parenthesis appears in both terms. We can factor this out to get open parenthesis, a plus 1 close parenthesis times open bracket, a cubed, plus open parenthesis, a minus 3 close parenthesis close bracket. Now, we'll simplify the expression inside the brackets. We have a cubed plus a minus 3, which can be written as a cubed plus a minus 3. So our final factored form is open parenthesis, a plus 1 close parenthesis times open parenthesis, a cubed plus a minus 3 close parenthesis. Let's move on to our second example. We want to factor the expression x to the fourth minus 10 x squared y squared plus 9 y to the fourth. For this type of expression, we'll use a different approach. First, we'll rewrite the expression as x squared squared plus open parenthesis negative 10 y squared close parenthesis times x squared plus 9y to the fourth. We notice this has the form of a squared plus b times a plus c, whereas x squared, b is negative 10y squared, and c is 9y to the fourth. To factor this, we'll rewrite the middle term as negative 9 y squared times x squared minus y squared times x squared. Now we'll group the terms. We group x squared squared plus negative 9 y squared times x squared, and negative y squared times x squared plus 9y to the fourth. For the first group, we can factor out x squared, giving us x squared times open parenthesis, x squared minus 9, y squared close parenthesis. For the second group, we can factor out negative y squared, giving us negative y squared times open parenthesis, x squared minus 9, y squared close parenthesis. Notice that x squared minus 9, y squared appears in both terms. We can factor this out to get open parenthesis, x squared minus 9, y squared close parenthesis times open parenthesis, x squared minus y squared close parenthesis. Both x squared minus 9y squared and x squared minus y squared are difference of squares, which we can factor further. X squared minus 9 y squared equals open parenthesis x plus 3 y close parenthesis times open parenthesis x minus 3 y close parenthesis. And x squared minus y squared equals open parenthesis x plus y close parenthesis times open parenthesis x minus y close parenthesis. So our final factored form is open parenthesis x minus 3, y close parenthesis times open parenthesis x plus 3, y close parenthesis times open parenthesis x minus, y close parenthesis times open parenthesis x plus y close parenthesis. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.